SwayamPrabha. Digital India. Educated India.
Welcome to lecture 29 of the course on multivariate data mining methods and applications. The title of this lecture is Centroid and non-hierarchical clustering methods. So, first we are going to discuss the centroid clustering. In centroid clustering, each cluster is represented by the mean of each and every variable. While calculating the distance between two clusters, we use the mean vectors of two clusters. We will also discuss the median clustering, which is usually more robust than the clustering method based on the mean vectors. Then whenever we merge two clusters, obviously there is some loss of information. Ward's clustering algorithm attempts to minimize such kind of loss of information. So, the basis of Ward's clustering algorithm to minimize the loss of information due to merging two clusters. We will discuss the Ward's clustering algorithm also in this lecture. Then we are going to discuss some of the non-hierarchical clustering methods. So, number of clusters in non-hierarchical clustering methods is prefixed, such as k-mean clustering, and then we cluster the observations into different groups. Now, agglomerate and divisive clustering. These are the two primary approaches. In agglomerate clustering, what we do? We start from here. So, initially we have the number of clusters equal to the number of observations, and in each cluster there is just one observation, and then we proceed iteratively. Here we are going to merge these two clusters or these two observations actually, and then at this stage we merge these two observations and so on, and ultimately we reach to a position where all the observations or all the clusters are merged in a single cluster. In divisive clustering, we start from a point where all the observations are in a single cluster. So, we start from this direction, and then we move downwards, means we divide this one cluster into two clusters, and then we move further until we reach to this point where each cluster has just a single observation. Agglomerative clustering is more commonly used because of its simplicity and efficiency. Now, we come to the centroid clustering. In centroid clustering, groups formed are represented by mean values for each variable. So, suppose there are two clusters. One cluster has observations on certain individuals, and for each individual actually we have multivariate observations means observations on several variables. Then what we do? We obtain the mean values for each variable. Say for group 1, we obtain mean values for each variable. So, ultimately we get a mean vector for group 1. Similarly, you can obtain a mean vector for group 2 also. Now, this group is now represented by the corresponding mean vector. And similarly, the second group is also represented by the corresponding mean vector. Then intergroup distance is defined as the distance between two such mean vectors. So, suppose the mean vector for this group is x bar 1 and the mean vector for this group is x bar 2. Then the distance between these two groups or these two clusters is actually the distance between their mean vectors, that is the distance between x 1 bar and x 2 bar. We consider this simple example. So, there are 5 individuals and on each individual we have observations on 2 variables. So, these are the observations. Then first we consider the Euclidean distance. So, the distance between individual 1 and individual 2 is equal to under root 1 minus 1 square plus 1 minus 2 square. So, we take simple Euclidean distance. So, for individual 1 and individual 2 corresponding to variable 1, we take 1 minus 1 and then we take square of this. Corresponding to variable 2, we take 1 minus 2 square. So, ultimately d12 is equal to 1. Similarly, we can calculate d13, which is 1 minus 6 square, that is 25, plus 1 minus 3 square, that is 4. So, under root 29. Similarly, you can calculate d24, which is equal to 7 and so on. So, ultimately we get this distance matrix d1. Now, we find the minimum distance. The minimum distance is 1 and this distance is between 1 and 2 individuals 1 and 2. So, in the first iteration we merge individuals 1 and 2. So, since d12 is smallest, we fuse 1 and 2. Then we represent individual 1, 2 or the cluster 1, 2 by the means of corresponding variables. Means for variable 1, we take the mean of these two, 1 plus 1 by 2, that is 1, and for variable 2 we take mean of 1 and 2, which is 1.5. Then the values corresponding to variable 1 and 2 for the individuals 3, 4 and 5 remain unchanged. Again we calculate d2. So, we get this matrix, distance matrix. Now, the minimum value is 2 and this distance is in between individual 4 and individual 5. So, at the next stage we merge individuals 4 and 5 at distance 2. So, after fusing 4 and 5, we represent this particular cluster by the means of corresponding variables, say 8 and 1. How we get 8? We take mean of these two, and then for variable 2 we take mean of 2 and 0. So, you get 1. Then for the first cluster 1, 2, the variable values are 1 and 1.5, for 3 it is 6, 3. Again we calculate the distance matrix and we get this distance matrix. Then the distance which is minimum is 2.83, which is the distance between 4, 5 and 3. So, in the next stage we fuse 4, 5 and 3 at the distance 2.83, and once we fuse 4, 5 and 3 we get these values. Say this 7 is the mean of values of variable 1 for 3, 4 and 5. Similarly, you get this 2 also. Again we calculate the distance matrix, this, and then at the distance 6.04 we merge these two clusters. So, ultimately we get a single cluster which is 1, 2, 3, 4, 5. So, all the individuals are now in a single cluster. So, ultimately we get this dendrogram. Now, we come to the median clustering. Now, some of the disadvantages of centroid clustering are: if sizes of groups to be fused are very different, then centroid of new group will be very close to the larger group and may remain within that group. Say, suppose one group is very large and another group is very small, and you are calculating the centroid for larger group and centroid for a smaller group, and then ultimately when we fuse these two groups, the centroid of the fused group will remain closer to the centroid of the larger group. So, this is the centroid for the smaller group, this is the centroid for the larger group, and when we fuse these groups, the centroid for the combined group is somewhere here, which is within the larger group, and it is quite close to the centroid of the larger group. So, in that case, the characteristic properties of the smaller groups are virtually lost. So, this is the main disadvantage of centroid clustering. Further, the centroid clustering is quite sensitive to outliers, because as you know, the mean is quite sensitive to outliers, and centroid clustering is based on the mean. In median clustering, if centroid of the groups to be fused are, say, I and j, then the distance of centroid of the third group, say H, from the group formed by I and j, when we combine I and j, then the distance of H from the combined group ij lies along the median of the triangle defined by I, j and h. So, we are actually using the median instead of mean, and this use of median makes the median clustering to be much less sensitive to outliers. Further, in place of Euclidean distance, which is the squared distance, the actual distance to the center is used. Now, we consider Watt's hierarchical clustering method. Now, whenever we merge two clusters, there is some loss of information, and the criterion for choosing the pair of clusters to be merged at each step in Watt's hierarchical clustering method is based on the optimal value of an objective function. And actually, in Watt's hierarchical clustering method, we minimize the loss of information from joining two groups. So, whenever we merge two clusters or two groups, there is some loss of information, and we measure that loss of information using the sum of squared deviations of every item in the cluster from the cluster mean, and then we try to minimize the sum of squared deviations. Now, suppose for a cluster K, ESSK is equal to sum of square deviations of every item in the cluster from the cluster mean. So, it is actually the error sum of squares. Then, for capital K clusters, the total error sum of squares is equal to the error sum of squares for the first cluster plus the error sum of squares for the second cluster, and so on, plus the error sum of squares for the kth cluster. So, this is total error sum of squares when we have capital K clusters. Then, in dendrogram, on the vertical axis we take ESS, and then vertical axis actually gives you the value of ESS at which mergers occur. Now, suppose you have the observation vectors, and for the first cluster the observation vectors are say x1, x2, xn, where x1 is equal to x11, x12, so on x1p, and so on, xn is equal to xn1, xn2, so on xnp. So, these are the observation vectors for the first cluster. And then x bar is the centroid. So, obviously, x1 bar is the mean of x11, x21, so on xn1, or you can say that x1 bar is equal to 1 upon n summation I equal to 1 to n x I1. In general, we define x bar j equal to 1 upon n summation I equal to 1 to n x I j for all j equal to 1 to p. Now, ESS 1 is equal to summation I equal to 1 to n summation j equal to 1 to p x I j minus x bar j square, and then you can write it as summation I equal to 1 to n x I minus x bar transpose x I minus x bar. So, for the first cluster, this is the error sum of square. Similarly, we can calculate the error sum of square for the other clusters also. Now, here are some comments on the hierarchical clustering procedures. Say, clustering method is sensitive to outliers. Well, some of the methods are more sensitive to outliers, whereas some other methods are less sensitive to outliers, like median clustering. It is less sensitive to outliers, but ultimately hierarchical procedures are usually sensitive to outliers. Then there is no provision for reallocation of objects that have been incorrectly grouped at any early stage. So, you can't revert the formation of your clusters. Once you have allocated an object to a particular cluster, and then you realize that it has been incorrectly grouped at some later stage, you can't do the allocation. Final configuration of clusters should be carefully examined. So, once you apply hierarchical clustering and then you get the final clusters, then this final clustering should be carefully examined. Then stability of clustering should be checked by applying clustering algorithm before and after adding small errors in data. Now, this is very crucial. Your clusters should be stable, and if there is some small changes in data, it should not affect the clusters or the formation of clusters. Clusters should be stable. And to check the stability of clusters, one of the option is you go for clustering and then you add some small errors in data. You randomly generate small errors and add those errors in the data, and again you apply the same clustering algorithm, and then you check the formation of the clusters. Whether adding small errors in data has any severe effect on the clustering, or the clustering remains unchanged. If the clustering remains unchanged, then you can say that your clustering is quite stable. So, if the groups are well distinguished, clustering should agree in both the cases, and this property is also called the robustness. So, in that case, if the groups are well distinguished and the clustering remains unchanged, when you add small errors in data, then you can say that your clustering is robust. Then one should attempt several clustering methods and distance measures and observe if results are consistent. So, before reaching a final decision, one must attempt several clustering methods, and one should use different distance measures also, and then observe how is it going to affect the results, whether the results are consistent or not. Then sometimes you may have ties. You may have, say, these two clusters, and then you have these two clusters at the same distance. So, there is a tie. So, one can combine these two clusters first and then move further, or another person may combine these two clusters first and then he move further. So, because of ties, multiple situations may occur. So, such kind of groupings should be properly interpreted, and different dendrograms can be compared to assess their overlaps. So, in case of ties, one may get more than one dendrograms, and then one may compare how much different their dendrograms are. An inversion occurs when an object joins existing cluster at a smaller distance than that of a previous cluster. So, this is another issue which one may face. The two clusters have merged at a particular distance. Then you have again computed the distance matrix. Then the next merger is at a smaller distance than the previous merger. So, this kind of situation is called inversion. So, sometimes inversion occurs with centroid method or median clustering. It is more likely that you get inversion in centroid method or median clustering. You do not get inversion in single linkage or complete linkage clustering, but it is very likely that you get the inversion in centroid methods. Now, this is the dendrogram with crossover. This merger occurs at a distance, say 30.5, and next merger occurs at a distance, say 30. Say here the distance between AB is 25.5, and after that the distance from C to this cluster AB is 30.5, and then you have this T, and the distance from D to ABC is 30.0. So, first you are merging A and B, and then since C is closer to AB than C to D, so we merge C with AB. But once you combine C with AB, the cluster ABC is at a distance 30.0 with D. So, you can say that there is a crossover or inversion. Now, we consider non-hierarchical or partitioning clustering methods. In hierarchical clustering, we do not prefix the number of clusters. How we proceed? Say, we initially start with the number of clusters equal to the number of observations. and then each cluster has a single observation. Then we keep on moving iteratively towards a single cluster including all the observations. And actually we merge different observations or different clusters at some distance. And then the problem is how to select the number of clusters. In non-hierarchical or partitioning clustering methods, we prefix the number of clusters. So, we have already decided the number, say capital K, of clusters, and after prefixing the number of clusters, we assign different clusters to different observations. Here actually we do not even define distance matrix, and this is the main advantage of this method. If you have large data set, then in the hierarchical clustering method, at each stage you have to obtain distance matrix based on large data sets. In this method actually you do not need distance matrix, so you can easily handle the large data sets. In hierarchical clustering, it becomes often it becomes difficult for you to handle large data set. So, we decide the number of clusters, then we initially select k seeds point randomly. So, you have say n observations, and ultimately your objective is to assign each observation a particular cluster. So, initially we assign different clusters to different observations randomly, or you can say that you select k seeds point randomly, and then we partition items in k clusters, and after that we add or leave points according to some criterion. We apply some criterion, and then we move the points from one cluster to another cluster, or we add and leave points according to the criterion. Now, we consider the algorithm for k means clustering. So, suppose this is your learning set or input data. So, your learning set is L equal to the set of points x size I equal to 1 to n, and your input is also the number of clusters k. So, as input you have the learning set as well as the number of clusters. Then initially what we do for the initial assignment of clusters, we form an initial random assignment of items into k clusters and compute current centroid for cluster k. So, randomly you have assigned the items to k clusters, then for each cluster you have computed the current centroid, say x bar k, for k equal to 1 to capital K. So, for each cluster we have computed the current centroid. Or another option is pre-specify k cluster centroids x bar k. You randomly pre-specify k cluster centroids for k equal to 1 to capital K. Now, at the next step, suppose x bar k is the kth cluster centroid. and Ci denotes the cluster containing the ith observation vector xi. Then we compute the squared Euclidean distance of each item to its current cluster centroid. We take each observation of the cluster and then we compute the squared Euclidean distance of each item to its centroid. We obtain ESS equal to summation k equal to 1 to capital K, then we take summation over Ci xi minus x bar k transpose xi minus x bar k. So, we compute ESS also. Then we reassign each item to its nearest cluster centroid, so that ESS is reduced in magnitude. So, again we do the reassignment of each item to its nearest cluster centroid, and then we update the cluster centroids after each reassignment. So, what you have done? You have computed ESS, then you have reassigned each item to its nearest cluster centroid. Of course, that item may remain in the same cluster to which it belongs, or it may switch over to some other cluster, and ultimately your criterion is ESS is reduced in magnitude. And once you do the reassignment, you again compute the cluster centroids. So, you update the cluster centroids after each reassignment. Then we repeat steps 3 and 4 until no further reassignment of items takes place. So, we keep on doing the reassignment unless the process stabilizes, in the sense that there is no further reassignment of items. Of course, up to some extent this final assignment depends upon the initial partition or seed points. Then, to check the stability, you may rerun the algorithm with a new set of initial groups. So, this is how you can go for k-mean clustering. Now, we consider this example. Say you have items A, B, C, D, and the observations x1, x2 means you have observations on two variables. Corresponding to A, you have observations 5, 3. Corresponding to B, you have observations -1, 1. Corresponding to C, you have 1, -2, and corresponding to D, you have -3, -2. So, mean for x1 is x1 bar equal to 0.5. You simply add all the values and divide it by 4. And for x2, the mean is 0. And suppose we are taking two clusters. So, k is fixed as 2. And initially, you take two clusters as AB and CD. So, this is the initial assignment. Then the centroids are for AB, the mean corresponding to variable x1 is 5 plus minus 1 by 2, that is 2. Corresponding to x2, it is 2. For CD, the means are minus 1 and minus 2. Now, what we do? We compute the distance of A from AB. We compute the distance of A from CD. Then d square AAB is equal to, this cluster AB is now represented by the mean vectors 2, 2. And for A, the observations are 5, 3. So, you have 5 minus 2 square plus 3 minus 2 square, that is 10. We also compute the distance of A from CD. So, you have 5 minus 1 square plus 3 minus 2 square. So, ultimately you get 61. Now, A is closer to AB. So, you do not move A to CD. A will remain within this cluster. Next, we calculate the distance of B from AB and the distance of B from CD. Again, the values of variables for B are minus 1, 1. So, minus 1 minus, then for AB the values are 2, 2. So, minus 1 minus 2 square plus the second value corresponding to x2 is 1. So, 1 minus and corresponding to AB it is 2. So, ultimately you get 10. Then we calculate the distance of B to CD and you get the distance 9. So, B is closer to CD than to AB. Now, we reassign B to CD. Then the two clusters are now A and BCD. A, BCD. Again, we represent this cluster BCD by the corresponding means, and then again we calculate the distances of A, B, C, D from the two clusters A and BCD, and then the distance of A from A is obviously 0, the distance of A from B is 40, distance of A from C is 41 and distance of A from D is 89. Whereas, the distance of A from BCD is 52, distance of B from BCD is 4, distance of C from BCD is 5 and the distance of D from BCD is 5. So, you observe that each item is now assigned to cluster with nearest centroid. Of course, 4 is lower than 40. So, B is closer to BCD than to A. Similarly, 5 is lower than 41. So, C is now closer to BCD than to A. Similarly, D is closer to BCD than to A. So, for k equal to 2, these are the two clusters. So, this is the final assignment. Now, we consider this example of k-mean clustering for the IRIS data set. This data set is built in R, and since we have already used this IRIS data set earlier also, so I am not going into the details of the data set. And then we have used R software for applying the k-mean clustering, and then we have used the library ggplot for plotting the data, and we get this plot when we use just petal length and petal width. And just by looking at this plot, we observe that there is some clustering pattern, or you observe one cluster here and one cluster here also. Then we have taken 3 clusters. So, k is fixed as 3, and then we have applied the k-mean clustering, and ultimately we obtain 3 clusters of sizes 48, 50 and 52. We have used just 2 variables for the clustering purpose, petal length and petal width. And then cluster means are for petal length. These are the means for 3 clusters. For petal width, these are the means for the 3 clusters. And then we get these clustering vector. Then we get within cluster sum of squares by cluster, and if we take the ratio of between sum of square to total sum of square, it is 94.3%, which is quite high. Now, we form a table with the species column of the original data just for the comparison of the results. So, we get this table. So, we have some of the observations which are in the wrong cluster also, or which are misclassified. Say here, and then we have here. So, all 50 points of the Sentosa variety were put in the 3rd cluster. Versicolor points were placed in the 1st cluster, but 2 points were classified incorrectly. You observe here these 2 points. Then Virginica variety points are classified into the 2nd cluster, and in the Virginica variety 4 of the points were classified incorrectly. These points, say 46 points are correctly classified and 4 points are incorrectly classified. So, the accuracy of the model is, say 50 plus 48 plus 46 by 150, which is 0.96 or 96%. So, you get 96% accuracy for the model. Then we have plotted the clusters. Say the cluster 1 is denoted by these red points, cluster 2 is denoted by these green points, and 3rd cluster is denoted by blue points. So, you get the plot of 3 clusters here. So, in this lecture, first we have discussed some hierarchical clustering methods. So, we have discussed the centroid clustering, median clustering and Ward's clustering algorithm. In centroid clustering, we represent a particular cluster by the means of different variables. And then before the next step, we take the distance between two clusters as the Euclidean distance between mean vectors of the two clusters. Usually, the centroid clustering is not very robust. So, we move to the median clustering, which is more robust than the centroid clustering. Median clustering is based on the median distance between clusters. We also discussed the Warts clustering. In fact, whenever we merge two clusters, there is some loss of information, and that loss of information may be measured by the error sum of squares. So, while merging the clusters in Warts clustering, we attempt to minimize the error sum of squares. Then we discussed some non-hierarchical clustering methods. In particular, we have discussed k-mean clustering. In hierarchical clustering, we do not prefix the number of clusters, whereas in k-mean clustering, we fix the number of clusters and then we assign the observations to different clusters using some criterion. Say initially we select some seed points, we assign different observations to k clusters, and then we move the observations from one cluster to another using certain criterion. And then we have also discussed an example in which we have applied k-mean clustering, and we have used our software for solving the example. So, I am going to stop here. Thank you.
Hello everybody, welcome back, and here I am to give a preview, very short obviously, in the area of what we mean by operation research and optimizations. So, we know operation research and optimization is used generally where you have some resources and you want to utilize them in the best possible way considering what your main objective is. Now, if we stop here and go back in the past, so the obvious question comes, from where did this technique of operation research and optimization, which is an area of mathematical techniques, come into the existence. So, generally even though the work has started from areas of mathematics, economics, but generally it is considered that operation research and optimizations were very heavily used and it became popular during World War II in trying to schedule different resources, manpower, armaments, considering there were resource constraints, time constraints and space constraints and so on and so forth. Now, for the general public, it should be aware that we consider from the academic point of view, there are different people, very famous people who have worked, but George Danzig is considered the father who really proposed the technique of linear programming as a very nice tool where you can use operation research techniques in order to optimize the resources which are there depending on different constraints which you have. And after that, things have really moved very fast. they have been developing throughout the world, they have been usage, they are different type of societies, so on and so forth. And in course of time we see and we still find exciting areas of application, but theoretically there has been a growth in techniques like robust optimization, stochastic optimization, dynamic programming, parametric programming, nonlinear programming, so on and so forth, and they are used depending on the concept and the areas of application which we see for either finance, for marketing, for scheduling, for engineering field, and so on and so forth. Now, application of OR and optimization, if somebody asks, is a very difficult question to answer, because if I start now, it will almost take about 1 hour to give you all the areas of application of optimization operation research are. But to keep it very brief, considering that you are all ready and eager to take that as a subject, I will just highlight the areas of applications, some of which are in scheduling, in assignment problem, in facility location, like you want to build up a factory, you want to build up some storehouse, so on and so forth. It is used in network flows, like you want to transport some goods, transport manpower from one area to another area. So, how we will try to basically do it in the best possible way. What is best would obviously depend on how you are trying to use optimization as a tool in different areas. It can be used, operation research and optimization can be used in health services, in financial portfolio management, asset liability management, game theory, and so on and so forth. Now, in the recent past, even though it is very well known, but still I would like to highlight the point that the computing powers and the techniques of operation research and obviously in statistics has exponentially grown. And with very sophisticated programming being available, like we know that there is MATLAB, there is R, there is SAS, which are different type of optimization tools. We see nowadays that operation research and optimization is also used in health sciences, in gene replication theory, in area of say for example prediction of weather, in the area of say for example prediction of earthquake, how you find out the best possible way to take actions such that it meets your overall demand. Say for example, in prediction of earthquakes, you would like to basically build up your houses, build up the dams, build up the overall locations of people staying in different localities in such a way that the minimization of the losses are sustained. Furthermore, after the advent of computing and advent of different techniques, we see many meta heuristic and heuristic techniques are very heavily used in parlance of operation research and optimization by joining them together such that you get the best benefit. So, if the question arises what are the meta heuristic techniques, I would again be very brief, because again there is a huge amount of literature, huge amount of application areas, huge amount of research which are being done in the area of genetic algorithm, taboo search, ant colony optimization, simulated annealing, then in the area of particle swarm optimization, in the area of artificial immune system, and so on and so forth. In the coming years, it is thought, and definitely with some positive viewpoint, that the area of multi-criteria decision making and multi-objective programming, where you use different type of tools and use the different advancement of optimization which has been made in such a way that you can basically optimize two different objective functions which are there in front of you, such that either if considering the area of finance, you can either maximize your return for the portfolio or minimize the risk also, or say for example you want to basically have a layout such that minimization of cost is one factor and the maximization of say for example benefit which accrues to different type of users in this overall layout can be attained at the same time. So, obviously it means that what we are seeing is a huge application of optimization along with different type of computing and heuristic techniques, such that in years to come this area of optimization would become one of the best tools where you accrue and get the benefits in the best possible way. And I am sure that the students or the participants who will take this course will find it an exciting add-on to their CVs and to their curriculum vitae, such that they can understand the techniques, how they can be used in the best possible practical sense. Thank you.